All right, this is my lecture from my notes on torque. We're starting a new unit and we have to learn a new topic. And the first topic is torque. Torque is a vector quantity that measures the effectiveness of a force that is causing rotation. So vector quantity, once again, is an quantity that has both direction and magnitude. The symbol used is a Greek letter tau, and it looks like a fancy T. The equation for torque is given there. The equation for torque is the moment arm times the force, and also equals the distance away from axis of rotation times force times sine of theta. We're going to understand those here more clearly with some examples. The unit of torque is a Newton times a meter. Don't be confused. A Newton times a meter is also a joule, but that's an energy term. This one we leave as a Newton meter, and that means torque. So let's talk about each item in the equation. Force is F is the force that's causing the torque. R perpendicular is called the moment arm or the lever arm. And what we find is that the moment arm is equal to R times sine theta. And that's actually what we'll use more than the moment arm. R is the position vector from the axis of rotation to where the force is applied. So we need to know where the force is applied and how far it is away from the axis of rotation. Theta is the angle between the direction of the force and the direction of the R vector, very similar to the work equation where work is equal to FD cosine theta. Theta is the angle between those two vectors. Theta in this equation is the angle between those two vectors. So very similar. Torque is a vector, has both magnitude and direction, and the equation will determine the magnitude. Okay, unlike the work equation, cosine theta determines whether it's positive or negative. This does not. This only determines the magnitude. We will have to know the direction. It is properly determined by what we call the right-hand rule. However, in AP and in honors, we will call positive torque torque that causes an object to rotate in the counterclockwise direction. That's standard in our math classes, and negative when it causes an object to rotate clockwise direction. However, sometimes the problem will reverse those in AP, for example. So pay attention to the information. Just like an axis can be positive to the right, it could also be negative to the right depending on the problem. So we get to choose that. But common notation is positive counterclockwise, negative clockwise. The axis of rotation I've already stated once, and that is the point at which the object rotates. The fulcrum is a pivot point. We're going to see that. This is a vocab discussion. So here is a seesaw sitting on top of a fulcrum. That is a pivot point. That's the axis of rotation will be there. Now let's do some examples so that we can utilize this equation. Torque equals FR sine theta. A force of a force of 10 newtons is applied at 0.5 and 2.5 meters from the axis of rotation. Here's the axis of rotation here. You may not be able to see it, but that 2.5 is this entire distance. That is 2.5. And then this little distance right here, that blue is, the 2.5 meters, and the yellow is 0.5 meters. Determine the torque by each force. So we'll call this, I'll show you my technique. This will cause that axis to rotate, or that bar to rotate about that axis in a clockwise direction. So that is negative torque. I'll call it torque 1 since it's the distance R1 from the axis of rotation. This also causes the torque to rotate in a clockwise direction. I'll call that torque 2. Torque 1 is equal to force A times R1 times sine of the angle between the force applied and the R. So here's the force applied and there's the angle. So hopefully you can see that that is 90 degrees. So we're going to quickly see that we can ignore that. So 10 newtons times R1, which is 2.5 meters, times sine of 90. Sine of 90 degrees is 1. Okay, so we can't ignore that. This will be 25 Newton meters. All right, that's a negative, by the way. The sine of 90 will not tell you that it's negative. You have to know that it's negative on your own. It's negative because it causes the bar to rotate in a clockwise direction. That's standard direction notation. All right, next one. We got torque 2. It is equal to FA, which is also 10 newtons, times R2, which is 0.5 meters, times sine of 90 degrees. It is 90 degrees between the R vector and the F vector. Okay, so if we multiply 10 times 0.5, we get 5 Newton meters. And that is negative as well. Next one. A force of 10 newtons is applied at 2.5 meters from the axis of rotation, and per the sketch, at an angle of 120 degrees, determine the magnitude of torque. Torque is equal to, oh, they said magnitude, so I didn't really have to, oh, no, the up top, number 1, did not say magnitude, but anyway. All right, so here's the R vector. Let me draw that. There's the R vector. There's the force applied. Okay, theta, they told me, was 120 degrees. Here's the angle between the two, and I'm going to talk about that in just a minute. So which angle do you use? Do you use 120 or do you use 60 degrees? Well, sine of 120 degrees is equal to the sine of 60 degrees. I believe those are called supplementary angles. So it really doesn't matter as long as it is one of the angles between the R vector and the force applied vector. So that's a good, you don't have to stress too much about that. Let's finish this. This is 10 newtons. That's the force. The R value is 2.5 meters. The sine of, I don't know, which one would you like to use? I'll say 60. That's probably the one I would have picked. And that will be equal to 21.65 Newton meters. Now this force will cause the torque to be in the clockwise direction, so that is negative, although it did ask for the magnitude. So it'll be a negative 21.65, and the answer, though, is 21.65 Newton meters. Number 3, a force FA is applied to 2.5 from the axis of rotation per the sketch. So here is my force. I'm pushing on it inward like that. Okay. So I've got essentially FA running right through the axis of rotation. Okay. And so there's my F. Let me think. I think I got it now. Sorry, excuse me. Yeah. And then there's my R value, or my direction of my R. And so a lot of people will say, okay, well, that is 180 degrees. Not a lot of people. That's the angle between the two vectors, 180. And so sine of 180 degrees is equal to 0. So the torque caused by that is equal to 0. Now I will quickly reference the fact that because that force runs right through the axis of rotation, as you can see, if we push on a door at the end like this is doing, if the force is directed towards the axis of rotation, that force does not cause a torque. Now I want to talk about moment arm real quick because that was part of that original torque equation. There's the moment arm times force. What is the moment arm? This is a force A applied at some distance r at the angle theta. And the moment arm is you have to draw a vector from the axis of rotation and create a 90-degree angle with the vector direction of the force that is being applied. Then you can find what that moment arm is. And I know that this is alpha. No, yeah, alpha and omega. We will call that sine of theta. And yes, it looks like it's the alpha angle, but don't forget the sine of supplementary angles. It's the same, and they define it as sine theta. Okay. Okay. We will never use that. I don't use the moment arm because it's more confusing. I will always use the RF sine theta, and hopefully that makes sense. Okay, a couple more examples, and then we're done for today. This is an example where we have two torques, and they have asked to determine the net torque. So I actually have three torques, excuse me, on this, and we have a hinge here, and this is the axis of rotation. I'm going to go label torque. This will be, I'll call this torque K. I'll call this torque R. I'll call this torque G. This is how I do it every time I'm trying to find torques. Why do I label it? Because I need to determine the direction of the torque. Is it positive or negative? This is going to cause that to go in a counterclockwise direction. That is positive. This is going to cause that to go in a clockwise direction. This is negative. This torque K actually goes through the axis of rotation, so the R value is 0. There is no distance away from the axis of rotation, so it's 0 torque. So if I want to know the torque net, I have to add all the torques up. I start with the positive torque, which is torque R, subtract by torque G. Now let's actually determine what torque R and torque G are. Torque is equal to the force times R times sine theta. So we have torque R, or force R, is 160 newtons. This is an equals, not a minus. Okay, 160 newtons times the distance away from the axis of rotation. That is 0.74 meters times sine of what angle? And this is actually where students will make mistakes. This is the R vector. Here is the angle that we need. So it's 35 degrees plus 90 degrees. And that will be sine of 100 and... Oh. I did it different ways. Hold on. I use this angle right here. This angle is 35 plus 90, which is 125. This angle inside is 55 degrees. Doesn't matter which one you use. I can use either 125 or 55 degrees. You're going to get the same answer because sine and supplementary angles are equivalent to another one. Then I have to subtract torque G, which is a negative, right? So that's why I subtracted it. And I have 170 newtons times the distance from the axis of rotation, which is 0.37 meters, times the sine of, all right, which angle? So here's the R vector, here's the force vector. We don't know this interior angle or this angle. We just know this little one inside. So we either have to add 90 degrees to 25 or subtract 25 from 90. So I added and found this one, which is 25 plus 90, and that will give me 115. And then I will plug that into my calculator, and I get 39.3, a positive 39.38 Newton meters. If I wanted it in 2 sig figs, because this is a flipping physics, I would have to have 4.0 times 10 to the 1 Newton megas, and that's 2 sig figs. All right. This is our last example for today. Two disgruntled business people are trying to use a revolving door, which is initially at rest. The woman on the left exerts a 625 Newton meter perpendicular to the floor. 625 Newton force perpendicular to the floor, 1.2 meters from the hub center. Let's fill that in then. I know this is 1.2 meters. I know this is 625 newtons. And then the guy is going to put 850 newtons. And then we know this distance in here is 0.8 meters. They're both perpendicular, so they have sine of 90, okay? We want to know the net torque and will the door remain at rest. So we'll call this torque 1. I'll call this torque 2. Torque 1 is actually going to be a negative torque because it's going to cause the door to rotate in a clockwise direction. Torque 2 is a positive torque because it's going to rotate in the counterclockwise direction. The net torque is the two of them added together, so torque 2 plus a negative torque 1. And now I will calculate the torques. Torque 2 is 850 newtons times the distance away from the axis of rotation, which is 0.8 meters, times the sine of 90 degrees, which is 1, minus torque 1, which is 625 newtons, times the distance away from the axis of rotation, which is 1.2 meters, times sine of 90 degrees, which is a value of 1. That'll equal a negative 70 Newton meters, which means, yes, it will rotate. Yes, it will rotate. It will actually have a negative angular acceleration. If the net torque is negative, the angular acceleration is negative. And it will rotate in a clockwise direction. And so how you would show that is like this, clockwise direction, okay? That's the end of the lecture today, where we have introduced torque and how to calculate it and some examples. Have a wonderful day. Come see